While any last stragglers come in, I want to talk about a couple questions and common errors that people were making on the last homework and with the IPython notebook, so I'll try to clear that up. The first thing with the IPython notebook, the order of things on the page can actually wind up being a little bit deceptive if you're sort of skipping around between the cells. So let's work through a quick example that'll hopefully illustrate how to properly think about what's actually going on under the hood. Right, we've got a cell and we type A equals 5, then we type print A. What's gonna come out on the output? 5, right. And specifically it's going to say out 0, maybe it says out 1, I forget, but the first output is going to say 5. All right, so then what if we make a couple more cells below? Just with that insert cell button here, you just go down to the next cell that's already in there in the homework or something like that. And we do A equals 7, print A. What is the output going to be now? Okay, that seems usable. So it's going to say out 1, so the second thing that we printed out. It's going to be 7. Okay, so now the pop quiz. We go up to here. If we click on this cell, this one, and then we hit Shift-Enter to execute this statement again. What's going to pop out here? 7. Why is that? Yeah, because A can only be one thing at a time. So, and more importantly, it's going to say out 2. So the outputs are ordered in time, not in space. The state of the program is in time, not in space. And usually, if you just go from top to bottom, time is the same as space and everything's fine. But if you go back and correct some error, you've sort of gone back in time. Or you've gone back in space, but you haven't gone back in time. So the things that are down below aren't going to magically get that error corrected unless you run them again afterwards. So generally the best thing to do is, if you have to go back and correct something, there's a menu that says run all cells, and it'll just start at the top and go all the way down. Or run all the cells above where I am, or all the cells below where you are. So that way you make sure that your notebook is always in a consistent state, and you don't have sort of old stale output hanging around that doesn't actually reflect what the latest value for all the variables is. Does that make sense? If there are any questions about that, ask me or any of the TAs who come to the help session, and we can play around with this until you get an intuitive feel for how it's going. Because this is sort of the one confusing part about the notebook. All right, so next. The homeworks have been graded. Homework number 1 is graded and back to you. Look at the comments on the blackboard. Mangi did a really nice job about commenting why things weren't working, giving you things to think about if you want to understand better what didn't work. We've posted the answers. Overall, everyone did really well. If you have any questions, email me or Mangi. We'll get you straightened out, or go to the help session. And again, everyone did really well, but if anyone wants to try again, felt that there was too much programming that they had to learn at the same time as doing the basic homework, we'll have a late homework amnesty, just this one time if you really want to try again. But again, everyone did really well. I'm not particularly worried. I don't recommend trying again for a grade, but you might want to try again just to make sure you understand it. And in particular, I want to point out one common error that people made when calculating the variance and then the standard deviation, which is, of course, the square root of the variance. So a lot of people got this far. So, you calculate the mean, and then what's the variance? The variance is sort of, it has to do with the squared distances from the mean. So, you could say, okay, the variance of our data set, which is, data 0 through data point n, people would get so far as to say, okay, it's data 0 minus the mean squared plus data point 1 minus the mean squared, and so forth. So people would get this far, but a good fraction of folk forgot that the variance isn't the total distance squared from the mean, it's the average. So you have to divide by the total number. And this makes sense. The variance of your data, or the standard deviation of your data, doesn't get bigger when you have more data. It gets bigger when you have data that's spread farther apart. So remember, the variance is the average squared distance from the mean. And when you do an average, you always divide by n. Fairly straightforward when I put it like that, but you want to keep that in mind. Okay, last sort of administrative thing. Homework number 3 is going live tonight. It will involve both coding in IPython, using a data set very much like the one that you downloaded and worked up in the last course. And it will involve doing some plotting, again in IPython, in the notebook, and answering questions about probability that we're talking about today. So it's integrating a lot that we've already done. And I highly encourage everyone to make use of the help sessions. If you have any questions, why isn't this working? If you're trying to get started and something isn't working before that, post a message on the Blackboard forum. That way everyone who probably has very similar questions can see the answers, or email one of us. Anything's fine. We really want to make sure that everyone has a good intuitive feel for what's going on. Okay, so today we will talk about probability. So first off, what is probability? Like what do I mean when I say the probability of something is something, 16%? What does that actually mean? So I'm going to make 3 statements that all sound like they're talking about probability. I could say there's about a 16% chance of rolling a 4 with 1 6-sided die. That's a statement about probability. I could also tell you, given how dinged up your computer looks, I think there's about a 10% chance it's actually going to turn on. That seems like it's a statement about probability, but it's very different than talking about rolling the dice. And then I could also say, well, there's a 12% chance that Bernie Sanders is going to win the Democratic nomination. And these are very different statements. One is about something that you can repeat over and over again. If you roll a dice, if you roll one die 100 times, about 16 times out of 100, it's going to come up with the side 4 on the top. You can do that at home. We can't have the Democratic nomination 100 times. So what does it mean to say that Bernie Sanders has a 12% chance? It's not like the dice example. And then the computer booting up thing is even different yet again. You press the power button and either the thing is going to turn on or it's not going to turn on. You can press it 100 times and if the computer is broken, it's broken, and if it's working, it's working. So each of these are very different statements about future events. One, again, is repeating things over and over, and other are events that can't be repeated or don't even make sense to talk about repeating. So probability is really philosophically slippery. in some sense, the Bernie Sanders example or the computer booting up is more about like, how surprised will I be if Bernie Sanders wins the nomination or if your computer actually turns on? And this is called Bayesian statistics, which is sort of very philosophically distinct from the statistics where we talk about rolling a dice 100 more times in the future. That's frequentist statistics. And so, like I said, philosophically very slippery. It leads a guy, a philosopher named Clark Glimor, who is the father of Bayesian network analysis, which is sort of a mainstay in bioinformatics and many other statistical realms. He wrote an article, Why I Am Not a Bayesian. And then this other guy, Roger Rosenkranz, writes a reply that says, why Glimor is a Bayesian. So, I mean, and this is philosophy, not math, almost. So, for the purpose of this class, we're actually going to simplify things greatly. And then really, in most of your science, we can simplify this sort of fuzzy, slippery concept of what we mean by probability into a really simple case. We're not going to talk about the future. Let's just say we have some number of things collected in front of us. Some number of mice in a cage, some number of genes in a table that we downloaded. And we want to know what fraction of those things has a given trait. And we're going to call that the probability of that trait. So let's talk about that gene data set. We could calculate the transcript length from the gene data set. And so we could ask, okay, well, what is the probability that a given gene in our data set has a transcript length greater than 50,000 kb, or 50,000 base pairs? So first off, how are we going to write that? So what's the notation? This is the notation for the sentence that I just said. The probability of this event, the thing that's in the parentheses is called the event. And the event here is the case that the transcription length data field, the column, has a number that's greater than 50,000. So what does this equal? How can we calculate this? I'll give you a hint. It's a ratio. What goes on the top? Right. The number greater than 50 kb. And what goes on the bottom? Total number. Very simple, very clear, no strange philosophy. But there's a lot that we can do with this really simple definition. So the first thing, we're going to pick up basically where we left off and start talking about calculating probabilities from histograms. So I'm going to make up a really simple data set with like not very many genes in it, 10 genes. Out of my way. And so let's say this is the histogram of exon counts for some very tiny data set. One exon, 2, 3, 4, 5, 6. So there's 10 genes. And so remember, at the end of last lecture, we talked about how you can have a histogram with the raw counts, but it also makes sense to just divide everything by the total, and that turns it into probabilities. So since these are out of 10, the division is easy. I do believe that adds up to 1. All right, so let's just start with some really simple questions. All right, what is the simplest question we can ask. We can ask, so what is the probability that the number of exons in a gene in our data set is 4? What's the probability? 0.1. I mean, okay. You know, this is the event if it's 0.1. Number of exons equals 2. 0.2. Straightforward. And this is how we write that in the notation. We can also ask slightly more interesting questions. Okay, so what's the probability of the exon count being 2 or fewer? 0.3. And so another way of looking at that is the whole area that we're interested in here is 2 or fewer. And so together those add up to 0.3. All right. So that's simple. What about we start combining a couple queries? So probability, what should be? The probability that the number of exons is between 2 and 5, inclusive. I heard it pointing. And again, just going to shade the areas. Okay, so what does it actually mean to say the probability is between 2 and 5? Can we break that down into simpler statements?
Greater than equal to 2 or less than equal to 5, and less than equal to 5.
There you go. So this is equivalent to saying something with an and. Okay, so let's look at how the area thing works. Fast running out of colors. All right, so where should I shade for exons greater than or equal to 2?
2 to 6.
All right. Okay, where should I shade for exons less than or equal to 5? Okay, so what is the and area? Yeah, it's the intersection. It's what I've shaded both. So the area where they're both true is the intersection of those. Okay, not rocket science yet. Let's talk a little bit about notation. How do you see and written? I just wrote it and. So sometimes you'll see and written like this. That's the symbol for intersection, which makes sense because it's an intersection. You might also see and written like that. That's a logical notation for and. And in computers, you might see and written like that. What's that? Ampersand. Why does the ampersand mean and? Anyone know? Does anyone know what et al. Means?
And everything else.
And everything else. And so it's short for et alia. So what does et mean?
And.
And. Et is Latin for and. I don't like this way of drawing an ampersand, by the way. I think it looks a lot nicer written like that, which you might have seen before. What does this look like? E-T. It was medieval monks who were lazy and they had to write and a lot in Latin. And they got sloppy and their ets started looking more and more like this, and then eventually they started looking like this. This is like cursive for lazy monks. But so the ampersand means et. So it's literally just and. All right, there's our trivia for the day. Back to stats. Okay, so that was and. What comes after and? Or. All right, let's talk about or. Okay. Well, now I have to draw that histogram again because I fouled it up. Okay. So, what about the probability that there are 2 or 4 exons? Where should I shade for that? 2 or 4. Oh, right. Okay, so what is that probability? 0.3. Okay. What about the probability that exons are greater than or equal to 5 or less than 2? Where am I going to mark that? Okay, so that's 3. So far, it's looking like probability of A or B equals, how do we simplify that? What have we done so far? Yeah, add them. Probability of A plus probability of B. Does this always work? All right, let's contrive an example where it's not going to work. Well-contrived example. Okay, so let's just figure out the probability of the independent parts. What's the probability of exon being between 2 and 4? 0.7. How about between 3 and 5? So I mean, already there's a problem if we just add them, right? Can't happen more than 100% of the time. So what's the problem? We have an overlap. So what does that mean in terms of the areas? We double counted. And which area did we double count? The overlap. Okay. What's our way of writing the probability of an overlap? Yeah. So when there's an overlap, we double count it accidentally. So we have to subtract one of those away. So you guys have probably seen this before. But again, thinking about things in terms of areas and overlaps, I'm like, okay, you know, we've done some double counting, this is a problem. All right, so that's and or. And so what's the notation for or? So do you remember set notation, the intersection? What's the opposite of intersection? It's union. So this is one notation for or. You might see it with the pointy or in computers. You'll often see a double bar for whatever reason. All right, so here we've got a fairly simple rule for or. Can we write a similarly simple rule for and? And I don't mean just, you know, move that around with algebra. How are we going to figure out how to calculate the probability of two things happening at the same time? Sort of in a principled fashion. To do that, we're going to look at an example from my personal area of expertise, worm breeding. That's my profession. I breed worms. Sometimes they're green, sometimes they're sickly, and sometimes, as we are going to see, they're both green and sickly. All right, so most of you are going to have to take a genetics class at some point, and I promise you this is going to be like the best part of genetics class ever, because worm breeding is basically high school biology. We're going to do a Punnett square. All right, so we have to get a little bit of notation out of the way first. There are things called genes. Genes have alleles, different versions of the gene. The one that most worms out there in the lab and possibly in the world have is called wild type, which we denote with a plus. So if a worm has two copies of a particular gene that are both wild type, we'll write that like this. So this is a gene named DAF2. On one chromosome and on the other chromosome, we've each got the wild type copy. Somewhere else, on another chromosome, this particular worm has something interesting. DAF16 fused to a GFP. Don't ask me how it got there. Magic. One convenient feature of worms, they are hermaphrodites. Makes strain maintenance easy. But they have optional males. Probably the best circumstance if you're a worm breeder. The males feel a little superfluous, but that's all right. So we can cross that to a male that has some loss of function allele at the DAF2 locus, and it's homozygous. But at this locus, we'll just call it, because this is sort of randomly integrated into the genome, it's, who knows where it is. We'll just call it the G locus. It doesn't have anything green. No green. And it's a male. Okay. What is the result of this exciting cross? Heterozygote. Okay, now this is too much letters, too many letters to write out, so I'm going to simplify this. So you've got one wild type and one loss of function at DAF2. And we've got one green and one not green at wherever in the genome that is. Okay. This is the miracle of worm breeding. This one's a hermaphrodite. It's self-fertile. We'll just let it fertilize itself. Done. Problem solved. So, oh wait, I never told you why we're doing this cross. You should probably know why you're doing an experiment, even if it's something your PI tells you to do. So we're doing this cross because we would really like to get the green GFP into the background of the DAF2 loss of function. It's probably one of the more famous crosses ever done in worms. And so we would like a homozygous for green and homozygous for DAF2 loss of function. So we've got this double head. All right. So now it's time for the Punnett square. What kind of eggs can this hermaphrodite make? Because remember, eggs have one, they're not diploid, they're haploid. So it's sort of a choose one and choose one. So I'm going to write that up here. So we could choose the top one and the top one. We could choose the top one and the bottom one. And so forth. Oh dear. We fit. All right. Okay. What kind of sperm can this worm make? Same. This is the most boring Punnett square in the world. So I'm just going to write these same down. Okay. So I'm going to put an X where they're homozygous, where the worm is homozygous for the GFP, and an O where where an offspring is homozygous for the DAF2 loss of function. Sound reasonable? Where should I put the X's? Does an X go here? X goes here. X goes here. X goes there. Everyone in agreement? Right, I know. High school biology. You guys are graduate students. Why am I going so slow with high school biology? Where do I put the O's? We want the loss of function. 2 copies of the loss of function. Okay. All right, so what is the probability of X? 1/4. Well, I mean, to me it looks like it's 4/16, but I guess 1/4 will do. Same thing with probability of O, right? So let's just write that out. So what's the probability of X and O? 1/16. Does this suggest to us a rule for how to get X and O from the probability of X and the probability of O? Okay, all right. So let's write this candidate rule down. Probability of A and B equals probability of A times probability of B. It works in one example. I think that deserves a question mark. Let's try two examples. It seems silly to have to pick a whole bunch of worms to try to find that 1 out of 16 worm. Can I make my chances any better? Is there something obvious about some of these worms that might allow us to exclude a portion that we're not concerned with?
They're green.
They're green, okay. So, now, it's actually really hard, it turns out, to tell the difference between one copy of GFP and two copies of GFP. So we can only tell green worms from totally not green worms. So, who is green at all? This worm is green. Actually, since they've got one copy, this whole row is green. This whole row is green. This column is green. And this column is green. So how many, I didn't draw that very well, but how many are green? 12. Okay. All right. So 12 worms are green. How many green worms are homozygous for green? 4. So 4 12ths. What is that? That's our X again. Four out of 12. Okay, what's our probability of O's now for just the green worms? Three out of 12, right. And what's our probability of X and O? Right, 1 out of 12. Does 4 out of 12 times 3 out of 12 equal 1 out of 12?
Yes.
Yes. Yes, it does. So that works. We've got two examples where this worked. But it doesn't always work. What if, has anyone heard of, raise your hand if you've heard of synthetic lethal interactions. So synthetic lethality is where an animal is totally happy with one copy of some messed up gene, and totally happy homozygous for one messed up gene, totally happy homozygous for another messed up gene, but if it's homozygous for both of the messed up genes, it can't recover. It's just too sick to live. And so that's called synthetic lethality. So in this case, this actually isn't going to be synthetically lethal because I mean, F16 GFP is probably not too sick. But you can imagine a scenario of synthetic lethality. So we're never going to observe these guys because they're dead. Well, actually, they're hermaphrodites. I'm not sure if you call hermaphrodites guys or gals. We don't have a good pronoun for them. All right, so let's do this calculation again. So, and we'll just stick with only the green ones. So what's the probability of homozygous GFP given that the worm is green? 3 out of 11, yeah. And same thing, probability of homozygous DAF2. 2 out of 11. What's the probability of getting both of them together? 0. Those don't multiply together. Is that correct? So what happened? Why didn't our simple rule work? So this is a fundamental concept in statistics called independence. This rule only works if A and B are independent. In fact, this is the definition of A and B being independent. That the probability of A multiplied by the probability of B is the same thing as getting both of them together. That A has nothing to say to B. And when these are just, completely isolated on different chromosomes and there's no interaction and worm isn't sicker with both of them than either, then they're independent. But if all of a sudden these two factors start interacting in some fashion, we can no longer guarantee independence. So for perhaps a more intuitive picture, think about other correlated events, other things that kind of happen at the same time as each other. So say we live in Seattle, and it's sunny out half of the time in Seattle. And about half of the time people carry umbrellas around with them. So what's the chance that you wake up and you see a sunny day with a lot of people with umbrellas on the street? Is it 50% times 50%? Is it 25% of the time? Probably not. There's a relationship between it being sunny and people carrying umbrellas. So that's what independence means. And now we're going to work through some more examples from the sort of a toy gene data set to understand better what independence does and doesn't mean in your actual data that you might see as a practicing biologist. But first to review, remember, probability of A or B probability of A or B is the sum minus the overlap. Probability of A and B is probability of A times the probability of B only when you are certain that they are independent. So with OR we basically add, but with a caveat. And with AND we basically multiply, but with a caveat. All right. Let's work through probabilities of some different gene characteristics. So I'm going to draw a couple histograms. Of a slightly more interesting toy data set. Okay, so in this data set of 1,000 genes, we can draw a histogram for the exon counts, 1, 2, and 3 exons. They're very little genes. And the coding sequence length in kilobases, from 0 to 2 kb all the way to 6 to 8 kb. So, to review, what is the probability of having 3 exons and having a coding sequence of less than 4 kb?